All right, welcome to Office Hours, where we'll be working through some example problems demonstrating some of the topics we discuss in qubits. For this video, we'll be focusing on solving a problem that involves constraint forces. Specifically, we're going to be using the tension force. And if you missed the introductory material, or you want a quick refresher on constraint forces, please check out the Physics QBit video linked in the description on constraint forces. Okay, so in the Physics QBit, we use systems that were at rest as our example systems. For our first problem for office hours, we'll do a problem with an object at rest as well. So imagine that you're at the park and you're hanging on the monkey bars. And let's say you're hanging in such a way that both of your arms make the same angle alpha with the monkey bars. And we want to know what the tension in both your left arm and your right arm are. Okay, so as per usual, because this is a force problem, we're going to start by using our four-step process for solving all force problems, beginning with a free body diagram. Then we're going to turn the free body diagram into a set of Newton's second laws. We're going to consider our constraints, especially because this is a constraint force problem. And four, we're going to solve our system and figure out whatever the forces we want to know are, right? Okay, so starting with the free body diagram, our simplified system looks kind of like just an object hanging from something with two tensions, right? So we have our first tension up and to the right, our second tension up and to the left, and we know that these vectors both make an angle alpha like this with a horizontal, right? What we can do immediately is draw an auxiliary line here, because we notice that because these lines are parallel, that means these angles must be the same. So these internal angles are all alpha. And there's one more force here. We know that there's going to be a gravitational force pulling down with some force, we'll just call it mg, where m is the mass of us, right? And so, because we've got our two contact forces as well as our gravitational force, this free body diagram should be good to go. Okay, next, we're going to work on our Newton's second law. So, we know that our Newton's second law equations are going to be equations that tell us about the forces in the x and y directions independently, so we had better be careful about the components here, right? So, if I look carefully at this, each of these diagonal vectors is going to have a horizontal component, which we'll draw out in red, and a vertical component that we'll draw in blue. And looking at this diagram, we see that these two will form vectors, or these two components will form legs of a right triangle, where the hypotenuse is going to be exactly the value of the tension like this, right? And so if we want to start by looking at the x direction, which is the red components, we can see that this component here for the right side tension is the adjacent side of our right triangle. And so we know that we're going to have a plus TR times cosine alpha, because cosine tracks the adjacent. Because the left tension is pointing to the left, then we know that, but has the same angle, we know that this is going to be TL times cosine alpha. And these two added together must be the net force in the F direction, which is m times the acceleration in the x direction, also by Newton's second law. Okay, the next thing we want to do is look at the vertical components. And so our diagram shows us there are three vertical components. And because these vertical blue components are opposite the angle that we've labeled, we're going to use sine instead of cosine. But we can see that the right tension gives us TR sine alpha. The left tension in this case is also positive because the blue component points upwards. So we have TL and also sine alpha, because once again, the vertical component is opposite the angle we've picked. And we also have a third force, which is the gravitational force, which points downwards. So we have minus mg. And these three added up make up all the forces in the y direction. So they had better tell us something about the net force in the y direction, right? Okay, good. So what I'm going to do now is take a second and ask you what you think the constraints on this problem are, and if you can express those mathematically. So take a second to work those out. Okay, hopefully you came up with that the constraints are the same as in our physics qubits, where we have the acceleration in the x and y directions are both 0. And those are exactly right, right? We're just hanging from the monkey bars here. There's nothing happening. We're not swinging. And so our net acceleration must be 0 in both directions. Okay, and so if we substitute these into our equations, then we find that our first equation gives us TR cosine alpha minus TL cosine alpha equals 0. And our second equation tells us TR sine alpha plus TL sine alpha minus mg equals 0. And so what we've got is a system of two equations, and our two unknown variables are just the tension in the right arm and the left arm. And we should be able to solve this. All right, so now that we have this copy pasted onto a fresh sheet, so we have some space to work with, remember our goal with solving two equations and two variables is always going to be starting with one equation and solving for one variable in terms of the other. That way we can eliminate it from the second equation and solve for just one variable at a time, right? So let's start from the first equation we have and try to solve for TR in terms of TL. So our equation reads TR cosine alpha minus TL cosine alpha equals 0. If I want to solve for TR, I can add TL cosine alpha to both sides. And we find that TR cosine alpha is exactly equal to TL cosine alpha. Then I can recognize that cosine alpha is on both sides of the equation. So I divide both sides by cosine alpha. These cancel out, and I get the final result that TR is exactly equal to TL. Okay, this is a nice intermediate result. This maybe shouldn't be so surprising because we're hanging from the monkey bars and our arms are kind of doing the same thing, right? Our arms are symmetric, and so it shouldn't be too surprising that the tension in our arms is the exact same. But this has the benefit of being able to be substituted into the second equation. Because we know that TR is the same as TL, then every time we see a TR, we can just replace it with a TL. Okay, so we find that the tensions in both our arms are the same. And maybe this shouldn't be so surprising, right? We're hanging kind of symmetrically from the monkey bars, so there's no difference between what our right and left arms are doing. But now that we know that TR and TL are the same, we can work with our second equation. And every time we see a TR, we can just replace it with a TL instead because we know they're equal, right? And so our equation will now read TL sine alpha after replacing the first TR plus TL sine alpha minus mg equals 0. Then, because I'm solving for TL, what I'm going to try to do is leave TL on one side of the equation. So let's gather our TL terms. And let's add mg to both sides. So that our equation now reads TL sine alpha plus TL sine alpha equals mg. Then we recognize that this is the same term twice, right? So this just becomes 2 TL sine alpha equals mg. And I can divide both sides by 2 sine alpha. And solve for TL, which is just TL is now mg over 2 sine alpha. And once I've gotten TL, remember earlier I solved for TR in terms of TL. So I can always take whatever result I get from solving the second equation and plug it right back into the first equation. That way we know that TR is the exact same as TL is exactly mg over 2 sine alpha. And then we're done. Okay, so remember that the tensions are a constraint force, right? So along this way, one thing that I want you to notice is that it was really important for us to be able to say that the constraints were that the accelerations in both directions were 0, right? If we didn't, what we'd have is two Newton's second law equations where both of the right-hand sides here and here would be m times ax and m times ay, which introduces two new variables, right? So we definitely can't solve two equations that have 4 unknowns. And so these constraints are really, really important, and they're the only thing that allow us to solve for what the tensions actually are. In our case, we found that the tensions are exactly mg over 2 sine alpha, and it turns out this is the only value that you can have for the tensions that maintains that the system isn't accelerating at all. And so as you go on and solve more of these problems in your homework or on exams, make sure to remember the important thing is isolating the constraints and being able to express them accurately mathematically. All right, that's all I have to say for this problem, really. In the next video, we're going to work on a problem where we don't get to use the at-rest condition, and we'll see what things look like if you have a system that's accelerating and not subject to a nice kind of easy constraint to work with. If you have any questions about any of the steps we took in this video, please feel free to ask in the comments with a timestamp just so I can follow along with your question. Don't forget to like and subscribe for more free physics problem solving tips. This has been Office Hours with Physics Tutoring Quantized.